Hey everyone, welcome to the next video from section 7.7. So this is going to be a fairly short video, I think, where I'm just going to wrap up the loose ends for how we solve diagonal systems and how we solve diagonalizable systems and sort of put those together into a nice package. And the video afterwards is going to be a full example showing all the theory from this section with one system. So let's go ahead and just start going on with how we solve diagonalizable systems. So first, let's mention briefly again solving diagonal systems. So this one, you had one of these on your previous worksheet question. If I'm trying to solve y prime equals, say, lambda 1, lambda 2 times y, this just turns into y1 prime equals lambda 1, y1, and y2 prime equals lambda 2, y2, because of how matrix multiplication works. And then we could just solve these directly using normal first order methods. Y1 of t equals y1 of 0 e to the lambda 1t, and y2 of t equals y2 of 0 times e to the lambda 2t. That's just how we solve this ODE like we did at the very, very beginning of this course. Well, so now from this, how do I get my general solution in terms of vectors? Well, my vector solution then is just going to be 1, 0 times y1 of 0 e to the lambda 1t plus 0, 1 times y2 of 0 e to the lambda 2t. Because when I put these together, I will get y2 being y2 of 0 e to the lambda 2t, and y1 being y1 of 0 e to the lambda 1t. So these are the solutions you get for these decoupled systems. Nice and easy, not too hard to do. So now, say we have a diagonalizable system. How do we go about solving that? So now I want to solve x prime equals ax, and A is going to be a diagonalizable matrix. So the idea goes like this. So I want to find a matrix T so that T inverse AT is a diagonal matrix D. In the last video, we talked about how you can do this, where if you find the n eigenvectors for A, you put them into a matrix, and that gives you a matrix T that does this. So I can find this matrix T, then define a vector function y by x equals t times y. So I can define y in this way because t is invertible, I can do this. And now I want to see what equation does y have to solve. Well, let's plug ty in for x on both sides of the equation up here. So I plug in ty for x, what do I get? I get t times y prime equals a times t times y. Now t is just a constant matrix, so I can move the prime through and just have the prime hit the y. So I get t times y prime equals a t times y. And if I multiply both sides by t inverse, this becomes y prime equals t inverse a t y. But this guy's diagonal. Y prime equals dy. So what we get out of that is y solves a decoupled system. So it's easy to get a solution. And then finally, we can get x from x equals t times y. So once I know y, I can multiply by the matrix T, and that'll give me my function x that I wanted from the beginning. And then x will solve x prime equals ax. So if I have a diagonalizable system, I can pick this matrix T and throw it at the problem, and that will give me a way to convert this into a diagonal system, which is easy to solve, and then I can work backwards to get my function x that I want out of it at the end. All right, so that's the point for this video, just getting you to how we can solve these diagonalizable systems using this diagonalization procedure. The next video is going to go through all the different theory from this section through a certain example. So I'm going to pick an example, and we're going to do the fundamental matrices. We're going to do the exponential stuff, maybe a little bit, probably not that. We're going to do this stuff with diagonalizable stuff as well. All right, so thanks a lot for watching this one, and I will see you in the next one with the example.